So I'm going to be giving a fairly general review talk on the topic of high-dimensional black holes, which is something I've been thinking about for the past 10 to 15 years. Clearly this is a subject in which we have to start with a bit of motivation. So there are various motivations one can give for the study of general relativity with extra dimensions of space, and for studying black holes in higher dimensions in particular. So historically, as Joe Brzezinski mentioned yesterday, Kaluza-Klein theory was a very attractive suggestion for how non-gravitational forces such as Maxwell's electromagnetism and Mill's theory could be obtained as geometrically from the dynamics of extra dimensions. So in Kaluza-Klein theory, one posits the existence of extra dimensions of space, which are supposed to be very much smaller than any length scale which is probed experimentally, explaining why they haven't been observed. So historically that was the first place where extra dimensions entered into general relativity. Now I said in Kaluza-Klein theory the extra dimensions which occur are compact, but I'm mostly going to be talking about extra dimensions which are macroscopic, so non-compact. And I think historically the first time that became important was in string theory discussions of black hole entropy. So Ted just gave us a very nice summary of the history of black hole entropy. So Hawking taught us that black holes have temperature, and this then combined with Bekenstein's ideas leads naturally inevitably to the conclusion that black holes have an entropy, but it doesn't tell us what the microscopic degrees of freedom responsible for that entropy actually are. So when we have an entropy, we would like to perform a statistical physics counting of quantum microstates in order to actually derive that entropy from first principles. So ever since the work of Hawking, it's been a challenge for quantum gravity to perform a detailed microscopic counting of quantum microstates and reproduce that formula for the entropy. And so this was achieved by string theorists about 20 years ago. But the first black holes whose entropy was calculated were certain supersymmetric black holes, not in 4 space-time dimensions, but in 5 space-time dimensions, 5 macroscopic asymptotically flat dimensions. Now these calculations subsequently were extended to other kinds of black holes, including 4-dimensional ones, but it remains the case that the 5-dimensional ones are the ones with the simplest microscopic description. And you could say that the more black holes whose entropy you have calculated, the more evidence you have accumulated in favour of your quantum theory of gravity, in this case string theory. And so it seemed an interesting thing to do to consider as many different black holes as you can in diverse dimensions and try and account for their entropy. Finally, we've heard about the ADS-CFT correspondence, the gauge gravity correspondence. So this famously relates strongly interacting quantum field theories in 4 dimensions of space-time to string theories, or general relativity, in more than 4 dimensions of space-time. And this is interesting for lots of reasons, but perhaps the most prosaic reason it's interesting is that it gives a new tool for performing calculations in strongly coupled quantum field theory. And higher dimensional black holes have played an important role in this connection. So, for example, 5-dimensional black holes in anti-de Sitter space-time have been used to explain certain properties of a quark-gluon plasma appearing in heavy ion colliders. For example, its low viscosity to entropy density ratio and the rapid thermalization of this plasma. So, higher dimensional black holes there are actually being used to obtain some insight into experimental results. So having said that, the focus of this talk is going to be on asymptotically flat black holes. For this I will need a negative cosmological constant. There's a whole story to tell there as well, but I don't have time. So I'm going to focus on describing black holes in more than 4 asymptotically flat dimensions. So those motivations were mainly physical, but there's maybe a more general motivation. So this is perhaps a more accurate reflection of my own motivations for thinking about general relativity in higher dimensions. And that's simply that general relativity is a very rigid theory. can do to it without destroying its basic properties. But one thing you can do is change the number of space-time dimensions. So if you like, you can view D, the number of dimensions, as a free parameter. And it's an interesting question to ask, what happens if we take D to be greater than 4? What changes? And what this can emphasize is properties of four-dimensional general relativity, which we should find unusual or surprising. It emphasizes what might have been possible in 4 dimensions. And we see what actually happens in higher dimensions. It may turn out that some things are simpler in higher dimensions than in 4 dimensions. So maybe there are certain calculations that one would like to do, which are easier to do it in higher dimensions, and then gradually work your way down to the physical case of 4 dimensions. And finally, as we'll see, it may be the case that there are explicit solutions available in higher dimensions, which may illustrate some important physical effect which is present for any number of dimensions. Okay, so that's motivation. Let's now start with describing some black hole solutions that are known in more than 4 dimensions. So the simplest kind of black hole in any number of dimensions is the high-dimensional generalization of the Schwarzschild solution, which has been known for a long time. So you just take the 4-dimensional Schwarzschild solution, and you simply replace the 2-sphere in the metric by a d-2 sphere. Okay, so then if you also change the radial dependence of the solution appropriately, so that the 1 over r is replaced by 1 over r to the d-3, then this gives you a solution of the vacuum Einstein equation. So it's a very simple generalization of the 4-dimensional solution. And it turns out that this is actually unique. So this is the unique, static, asymptotically flat black hole solution of the vacuum Einstein equation in any number of dimensions, 4 or greater. So it obeys the same kind of uniqueness theorems in 4 dimensions. Another similarity with 4 dimensions is the issue of stability. So people have considered linear perturbations of this solution and found that it's stable. More precisely, given the talk we had yesterday from Sergei Kleinemann, what's actually been proved is that there are no exponentially growing modes in this solution. So it's as stable as the 4-dimensional solution. So as far as static, asymptotically flat black holes are concerned, higher dimensions are essentially the same as 4 dimensions. Now one difference that can occur for static solutions occurs if we relax this assumption of asymptotic flatness. So a simple way of constructing new solutions of the vacuum Einstein equation is to take a product. So we can take a product of the d-1 dimensional Schwarzschild solution with a flat direction. So taking a product of 2 Ricci flat spacetimes gives another Ricci flat spacetime. So this will give us a solution of the Einstein equation. And since our d-1 dimensional Schwarzschild solution had an event horizon with spherical topology, this product spacetime will also have an horizon. And the horizon will have topology, the sphere times this flat direction, and we've taken the product. So it's an infinitely extended horizon with this cylindrical topology. So these are called black strings because they look like infinitely extended strings with a translational symmetry as we move along this direction here. So as I said, these are not asymptotically flat because the solution doesn't approach flat space as we move in this direction. So they're not asymptotically flat, but as we'll see, the existence of these solutions is going to guide our intuition for the properties of genuinely asymptotically flat black hole solutions in higher dimensions. I should then also emphasize that these solutions, of course, don't exist in 4 dimensions. The reason they don't exist in 4 dimensions is that there are no black holes in 3 dimensions. Okay, so for the rest of the talk, I'm going to focus on genuinely asymptotically flat black hole solutions in vacuum in higher dimensions. So I'm going to review for you now what the known solutions are satisfying these criteria. So I've told you about generalized Schwarzschild. Let me now tell you about the higher dimensional generalization of the Kerr solution. So this was constructed in 1986 by Myers and Perry. So they succeeded in generalizing the Kerr solution to any number of space-time dimensions d, And they did it essentially using the same methods that Kerr used to construct his solution in the first place. So, unsurprisingly, their properties turn out to be rather similar to the properties of the Kerr solution. So, just like Kerr, they're topologically spherical. Just like Kerr, they're uniquely labelled by their mass and their angular momentum. So there's one small technical difference in higher dimensions, is that you have to specify more than one angular momentum. The number you need is given by the rank of the rotation group, which is the integer part of v minus 1 over 2. So for example, in 5 dimensions, asymptotically flat solutions are characterised by 2 angular momenta. But apart from that technical detail, it's very similar to Kerr. Another similarity with Kerr is the existence of hidden symmetries. So these solutions have hidden symmetries associated to the existence of Killing-Yarnow tensors and Killing tensors, and these enable you to solve the geodesic equation, or the Wade equation, by separation of variables. Another similarity comes from the Petrov type of the Weyl tensor, so that the Petrov classification has been extended to higher dimensions, and the Weyl tensor of Myers-Perry, just like Kerr, turns out to be type D. Interestingly, it turns out that there's a kind of uniqueness result you can prove for Myers-Perry black holes for the special case of 5 dimensions, where one can show essentially that these solutions are unique amongst type 2 algebraically special solutions, which is certainly not true for the Kerr solution. So this is a rather unusual result from the property of Kerr in terms of the uniqueness of solutions with an algebraically special Weyl tensor. Okay, so those are the Myers-Perry solutions. What else is there? So the second family of vacuum solutions that we have to higher dimensional gravity are the black rings. So to understand what a black ring is, we can go back to these black strings I was describing earlier. So as I said, a black string is an infinitely extended object, but one can imagine taking a finite segment of black string and gluing the ends together to form a loop. Okay, so that will give an object that looks like this donut here, a loop-shaped horizon. Of course, this loop is now just going to want to collapse under its own gravity. So it would be unstable. But one can ask the question of whether it's possible now, if we make it rotate in the direction of the arrow, whether that can give rise to a centrifugal repulsion which balances the gravitational self-attraction of the loop and gives us a nice equilibrium solution. So surprisingly, it turns out one can actually find an explicit solution of the Einstein equation, at least for the case of 5 dimensions, which does exactly this. So there's an explicit 5-dimensional vacuum solution describing a black hole which looks like a rotating donut. So these are the black rings. So the most striking feature of the black rings is their topology. So unlike the Myers-Perry black holes, unlike the Kerr solution, these are topologically non-spherical. So the topology is a circle S1 times a sphere, where the circle is this direction and the sphere is transverse to it. So these are the first examples of topologically non-spherical black holes. Of course, in 4 dimensions, Hawking's theorem says that any black hole must be topologically spherical. Another important difference with 4 dimensions is that these black rings are not uniquely labelled by their mass and their angular momentum, unlike the Myers-Perry solution. So you can have 2 different black rings with the same mass and the same angular momentum. Furthermore, you could have a black ring, you could have 2 black rings, and a Myers-Perry black hole with the same mass and angular momentum. So this idea that we're familiar with in 4 dimensions, that stationary black hole solutions are uniquely characterized by mass and angular momentum, simply isn't true, at least in 5 dimensions, because we have this explicit counterexample. Okay, so what else is there? Well, here's a cute generalization of what we've just heard. So now that we have these Myers-Perry black holes, which are essentially higher dimensional Kerr, and we have the black rings, we can try to superpose them. So we can try to construct a superposition of a Myers-Perry black hole in 5 dimensions with a concentric black ring. And for obvious reasons, this is called black Saturn. So I said we can try to superpose them. Of course, the Einstein equation is non-linear. You can't just superpose solutions. There's a hard calculation to do using sophisticated solution generating techniques, specifically the Belinsky-Sakharov technique. But nevertheless, you can use that to construct an explicit solution describing such an object. And this is the first example of a regular stationary vacuum black hole solution with a disconnected event horizon. So this again is believed to be impossible in 4 dimensions. But here in higher dimensions we have a completely explicit solution that you can write down on a piece of paper, provided your piece of paper is big enough. So this also gives a nice illustration of a very physical effect in general relativity, which is the frame dragging effect. So we can take this central black hole, the Myers-Berry black hole, and set its angular momentum to 0. Okay, so this is 0 angular momentum. Nevertheless, it turns out that its angular velocity, as measured by the horizon generators, is non-zero. So it has 0 angular momentum, but non-zero angular velocity. And this is interpreted as due to the frame dragging effect caused by the rotation of the black ring. So the rotation of the black ring drags around the generators of the horizon of the central Myers-Berry black hole, even though it has 0 angular momentum. So this is a nice explicit solution which illustrates this physical effect in GR. Okay, what else is there? So here's a very recent discovery, just a couple of years ago. So now I'm going to break my self-imposed rule of only talking about vacuum solutions, and we're going to have a brief detour into Einstein-Maxwell theory. Or more specifically, I'm going to talk about a solution of 5-dimensional supergravity, which you can think of essentially as Einstein-Maxwell theory. So recently, Kanduri and Lucetti have constructed a completely explicit solution of this theory, which describes a 5-dimensional asymptotically flat black hole whose event horizon has the topology of what's known as a lens space. So lens spaces are certain discrete quotients of 3 spheres. So there are infinitely many different types of lens space, but they're all quotients of 3 spheres. And so Kanduri and Lucetti have constructed an explicit solution for 5-dimensional supergravity describing a black hole whose horizon has this topology. These are rather special in the sense that they are supersymmetric solutions, which means that their mass is equal to their charge. And this implies in particular that their horizon is extremal, degenerate, so that the Hawking temperature is 0. So they're rather special in that regard. But there's no reason why non-extremal solutions that generalize these shouldn't exist. It's just hard to find them. So this supersymmetry property was important in the method used to construct this solution. So if you focus on supersymmetric solutions, there are special techniques that can be exploited which simplify the problem of constructing solutions, and that's how they found it. But non-extremal generalizations should exist, at least in Einstein-Maxwell theory. What's less clear is whether vacuum solutions with this topology should exist. At the moment, that's completely unclear. Okay, what else is there? So far I've just spoken about explicit solutions that one can write down, but there's also been a lot of activity in constructing solutions numerically. And the focus here has essentially been on looking for stationary vacuum black hole solutions which have the same amount of symmetry as a Myers-Berry black hole, so it's a high-dimensional curve black hole. So in 5 dimensions, for example, the Myers-Berry black hole has 3 commuting Killing vector fields, so that amount of symmetry. And perhaps the easiest way of explaining what's been discovered is using this diagram, which comes from a paper of Enferel and collaborators a few years ago, which anticipated many of these discoveries. So this is a Myers-Berry black hole, and imagine this black curve here corresponds to moving along the family of Myers-Berry solutions by increasing the angular momentum. Okay? So we start off up here, which is basically Schwarzschild, we increase the spin, and eventually we reach this point here, where a new solution bifurcates from the Myers-Berry family. And that new solution has a kind of deformed sphere-type horizon, whereas a dimple has developed in the middle. These are called bumpy black holes, and they exist in 6 or more dimensions. So we've kind of put a bump into the middle of the Myers-Perry solution. We haven't broken any symmetries by doing this, we've just deformed the shape. It's a bit like changing the dependence on the theta coordinate in the Kerr solution. We then move along this new branch of solutions, we get to a point here where that bump actually pinches off like this, and the solution transitions to a black ring. And so this is in 6 or more dimensions. It turns out that the black ring solutions have been constructed numerically. So the only case for which we have an analytic black hole solution is in 5 dimensions, but in 6 or 7 dimensions, and in principle higher, we have numerical black ring solutions. And so these solutions are all connected by these different topology changing transitions as you move around. You can also get black Saturns and bumpy black Saturns and all sorts of complicated stuff. Another kind of black hole which has been found recently are so-called black ringoids, perhaps not the greatest name, but these are black holes that they've been constructed just for the case of 7 dimensions so far, but in principle they should exist in higher as well. The horizon topology here is a product, S2 times S3, a product of 2 spheres. These have angular momentum turned on in several directions. And so there's a whole zoo of different black hole solutions which have been discovered by various different methods. So we can now ask, is it possible to make sense of this zoo? Are there any general principles that we can use to organise these solutions? And there are. So one general result concerns the topology of black holes. So this is a picture of a knot from the entrance to my department. So it was the best picture I could find of topology. 10 years ago, Galloway and Schoen managed to prove a generalization of Hawking's topology theorem for any number of dimensions. And what the generalization states is that a cross-section through the event horizon, which is a D minus 2 manifold, must admit a metric of positive scalar curvature. It needn't actually have a metric of positive scalar curvature, but it needs to admit one. And this is a topological restriction on the horizon cross-section. In 4 dimensions, this implies immediately that the topology must be spherical, just from the Gauss-Bonnet theorem. And there's also a fairly simple list of possible topologies in 5 dimensions. So in 5 dimensions, the horizon cross-section is a 3 manifold. 3 manifolds with this property have been classified. Here's the classification. So one possibility is a 3-sphere, like the Myers-Perry solution. We could also have a quotient of the 3-sphere, black lens. We can also have S1 cross S2, which would be a black ring. So it's nice, these are they correspond to the solutions I've described so far, but there's a more unpleasant possibility, which is that of taking connected sums of these components. So a connected sum is a topological way of gluing manifolds together, and in principle you can glue arbitrarily many copies of these things together. So you can take 27 copies of S1 cross S2 and glue them to 35 black lenses, and in principle that's an allowed topology for 5-dimensional black holes, which of course is not realised by any known solution. And in more than 5 dimensions, there's no such explicit statement for the allowed possibilities. So that's topology. Another general result concerns the rigidity theorem, which was discussed yesterday by Sergei Kleinemann. So remember, Hawking's rigidity theorem says that a stationary black hole should be axisymmetric. And so this result has also been generalized to higher dimensions. So here's the statement: a stationary, rotating, asymptotically flat, analytic, vacuum black hole solution must admit a rotational symmetry. And I must confess that the word analytic was put in this morning after Sergei's talk yesterday. But this assumption is needed in higher dimensions just as in 4 dimensions. So the theorem does generalize to higher dimensions, although interestingly the proof is it's rather different in higher dimensions. But what's surprising is that all of the known higher dimensional black hole solutions have got multiple rotational symmetries. And all this theorem gives you is one rotational symmetry. So for example, in 5 dimensions, the Myers-Perry black hole and the black rings both have 2 rotational symmetries, not just the one that this theorem guarantees. And so if all known solutions have more symmetry than we have any right to expect on the basis of general theorems, then maybe there exist further solutions which haven't been discovered yet, which have got less symmetry. And of course, if they have less symmetry, it's harder to find them, which explains why we haven't discovered them yet. So you can look for such solutions using various techniques. Well, one way is looking at perturbations of known solutions. So one can look at perturbations of the Myers-Berry solutions, for example, linear perturbations. And it turns out that certain Myers-Berry solutions with particular values for their parameters admit a linearized perturbation which is stationary and breaks all but one of the rotational symmetries. So this can be interpreted as evidence for a new family of black hole solutions which is bifurcating from the Myers-Berry family and preserves exactly one rotational symmetry. And I'll mention some more evidence for this in a moment. Okay, so I've mentioned the known explicit solutions, and I've mentioned some solutions constructed numerically. Various perturbative techniques have also been introduced for studying black holes in higher dimensions. One goes under the name of black holes, and the starting point here is the observation that in higher dimensions, a black hole can be characterized by two very different length scales. So an example would be a black ring, where the radius of the S1 is much larger than the radius of the S2. So the ring looks like a hula hoop, where it's very thin with a large radius in this direction. So then we have a small dimensionless ratio, which is the ratio of this radius to this radius. And we can try to construct solutions perturbatively as an expansion in that small parameter. So this method has been used to construct various perturbative solutions. So one thing that's been done in 5 dimensions is to construct black ring solutions with just a single rotational symmetry. So previously I mentioned evidence for spherical topology black holes, which is one rotational symmetry. Using this method, black rings can also be found there. It can also be used to construct black ring solutions in more than 5 dimensions. So again, as I said, we only have an explicit solution for black rings in 5 dimensions, so this gives us a new way of constructing perturbatively black rings in more than 5 dimensions. Finally, it's given perturbative solutions with different topologies. So typically the kinds of black hole topology that can be obtained using this approach are products of spheres. Remember, we have to have a large hierarchy between length scales. Typically what you find is horizon topologies where you have a product of odd-dimensional large radius spheres with a small sphere. Okay. So a special case of this would be one of the black ringoid solutions I mentioned earlier. So these are the kinds of things that come out of this construction. A different perturbative approach which has been introduced very recently goes under the name of the large D expansion. So this is motivated by the question of whether general relativity simplifies when D, the number of space-time dimensions, is large. So this is motivated perhaps in analogy with the large N expansion of quantum field theories, where if you take a Yang-Mills theory with an SUN gauge group, then it simplifies a large N and becomes a string theory. So the question is there a similar kind of simplification in general relativity? So the basic idea is this: so we're in D dimensions, and we restrict attention to space-times which are foliated by symmetric n-dimensional submanifolds. So, for example, consider space-times foliated by n-dimensional spheres. We can then